studied theoretical physics at the EPFL and at the ETH, and then he did his PhD 2005 on quantum security, and then he did a postdoc at Cambridge University, and then since 2007 he is now professor at the ETH for theoretical physics, and he will talk today about discovering physical concepts using neural networks. So the stage is yours.
Okay, thanks very much. I would also like to thank the organizer for the invitation. It's always a pleasure to connect to people working on artificial intelligence, much more than I do. I do that out of an interest, and also out, as I will explain in this talk, out of a desperation. And I will make clear what I mean by that during my talk. So let me start the screen sharing. Okay, I hope you can see my slides. Yes. So the first slide is just maybe the most important one, namely to acknowledge all the people who contribute to the work that I'm going to present. And actually, I will not go into technical details in the following. Rather, my goal is to somehow explain why it comes that a person like me, who is mostly interested in the foundations of physics, and in particular the foundations of quantum mechanics, gets drawn into research on neural networks. And there is actually a nice, I would say, overlap that goes much beyond just the use of optimization methods to solve certain physics problems. It's also about conceptual understanding, and that's what I would like to talk today. So in particular, the work that I'm going to present is based on a by now pretty old, I think, in the standards of machine learning paper on discovering physical concepts of neural networks that I wrote with my former PhD student, Rabbaniten, and a PhD student I have now, Tony Metzger, and Henrik Wilming, who was a postdoc, and Lydia Del Rio, who was actually one of the persons who initiated all this. And then there's another paper together with the group of Hans Briegel, who gave a very nice talk yesterday, a bit a long one, but very inspiring one, and Nur Galieva, with whom I'm working on foundations. And we have a recent paper on the use of thought experiments. And if you're interested in some of the stuff I'm going to present in the first part of the talk, then this is maybe a good source to look into. I will show these references again at the end. So we'll start with something that not every participant of this workshop may be aware of, because I assume the audience is relatively broad, and the quantum measurement problem. This is, I would say, one of the most fundamental and still unsolved problems we have in physics, in particular in quantum physics, and it's about the following. So quantum theory is by now an extremely well-established theory, and I think no one doubts the fact that it probably all the predictions it makes are extremely accurate. That's experimentally confirmed. And despite this success, we have this open question that we actually don't know to which systems can we apply quantum theory. So what is, in a way, the subdivision of the world I have to make into the system to which I can apply quantum theory, and the part which is somehow the outside. So now you may ask, why do I even need such a subdivision? But if you look into quantum theory, it has a very strange feature. On the one hand, it says that there are quantum systems, and these quantum systems evolve in a completely reversible way, described according to unitary operators. But I mean, the point is this is reversible. And then we have something completely different. We say that we can also do measurements on these systems, and these measurements are highly non-reversible. These will, in an irreversible way, change the state of the system, but they will provide us with information about the system. And of course, if we do an experiment, we have on the one hand this reversible evolution of the quantum system, but at some point we have to make a measurement. And this measurement, because it's not reversible, is not described itself by the formalism which describes quantum systems. So the way to think of it, you could say, we have, whenever we apply quantum theory, we have to identify a subpart of the world that we could say is the quantum part. So I put the Q here. And then we have a classical part, that's the outside of the quantum system. That's everything that is not included in Q. And if we now apply the quantum formalism, this part evolves, first of all, unitarily, if it's a closed system. But then if you do a measurement, there's some information flow out of this quantum system to the outside world, to the classical world. And the big question is now, where do we make this cut? This cut is famously known as the Heisenberg cut. And the name shows that this problem was already discussed in the early days of quantum theory, not only by Heisenberg, but by many others, among them also Niels Bohr. So what's really now the problem? So we have a perfectly functioning formalism, but in order to apply it, we need to identify the system. And now the question is, where do we put this border? And now you see in this picture is a little fox. Now you could ask, should this fox now be inside the quantum part, or should it be in the classical part? So that would be another valid situation. You could ask, does it even matter? But clearly, I mean, it matters because the way we apply quantum theory to this larger part is different than if you only apply it to here. Maybe the results are the same. I will come back to that. There's a nice answer given to this question of how should we define this outer part and is it even needed? And I'll just read this citation because this is one of the, let's say, central parts of my talk. I call this the communicability. So what Niels Bohr said is that when we do an experiment, we refer to a situation where we can tell others what we have done and what we have learned, and that therefore the account of the experimental arrangement and of the results of the observation must be expressed in unambiguous language. And by language, you see here at the end of the citation, he refers to classical physics. So when we say something, when I say I measured this outcome, then I describe that in classical language, even if I'm talking about an experiment that involves a quantum system. So this gives us a kind of criterion. It tells us that this part is the part about which we can essentially talk with others. Now, in this particular setup, this doesn't really give us a criterion. Of course, Alice, I call her Alice in the following because there will not be another agent, Bob, will probably not talk with this fox here. So we could say that it's sufficient for her to treat that part here as the classical part. But now suppose you have a situation with more than one agent. So there would be now, I call her an inside agent, Alice, and an outside agent, Bob. And Bob may kind of put the Heisenberg cut here in between him and Alice. Or he may also choose, or Alice may, for example, choose to put the cut here and say that this whole part is the class. So one safe way to proceed is to say, Alice and Bob maybe want to talk at the end about the outcome of an experiment. So they should both be on this classical side of the cut. But maybe that's not always the right choice. It's certainly the right choice if they want to communicate, as I indicated here. So the blue arrows will always stand for communication. But there could also be another experiment you may do. And this experiment was considered also in the early days of quantum theory. It's not really a different experiment, but it's much more a different way of thinking about the quantum experiment. This outside agent could now put Alice, if you like, or this is also called, traditionally we call her the friend of the outside agent, into an isolated box. Now, from this outside viewpoint, if this box is isolated, we can anyway not talk with the person inside. It's perfectly legitimate to treat this entire box as a quantum system. And so we would apply these reversible operations, which leads, however, to strange conclusions, as Wigner already pointed out. So, for example, if this particle here is in a superposition state between up and down, and Alice is instructed to measure this particle in the up-down basis, then from the description, from the viewpoint of the outside agent, she will, and this measurement will be a reversible operation, bringing her into a superposition state where in one part of the state she has measured up, and in the other part she has seen down. This is related to the famous Schrödinger cat, which is in a superposition of dead and alive. Here it's just Alice who is in a superposition of having seen up and down. Now, this of course puts doubt on whether it's really a reasonable choice to say that this system here is a big quantum system, because it's kind of hard to think what it means that an observer is itself in a superposition. Now one could say that, I mean, maybe you have heard that there are different or many interpretations of quantum theory. And one could say the different interpretations of quantum theory are not really different in what they tell you about the formalism of quantum theory. That's why they're maybe called interpretations, but they're different in what they would tell you how to apply quantum theory to this experiment. So for example, just to give you an idea, there is one formalism, which is many worlds, which says, okay, now we need to clean this up and say, the best choice is if we just always consider everything as a big quantum system and have no classical part. So we kind of move this classicality to the outside, which of course creates many problems, because now we have nothing really to talk about in classical language, to use Niels Bohr's terms. Another possibility is to say, no, we always can only consider small systems as quantum systems, and everything else, agents, have to be classical. That would be, for example, the view of collapse theories. There's another view which says, which is quantum Bayesianism, everyone can choose his own Heisenberg cut. So it's fine if Alice says the cut is here and she just treats this as a quantum system, whereas the outside agent here says, no, this whole thing is a quantum system. So the different interpretations have different views on where to put the cut. Now this raises a question. I mean, now you can see this is one choice of the cut, and you can ask yourself, okay, if now the cut that Bob puts is a different one from Alice, can they still be consistent with each other? Now what was always believed to be true is, yes, we still have consistency, because, for example, in this experiment that I showed you here, as I said, there is an isolated box, so Wigner will anyway not be able to talk to Alice, so that they cannot detect any inconsistency. So even though, and the outside agent would say Alice is in the superposition state, and Alice would say, no, I've seen an actual outcome, I don't see a superposition of two. This is not the problem, because they would never be able to talk because of the isolation. And as soon as they would lift the isolation, this would mean that the outside agent would somehow carry out the measurement and destroy the state of Alice. So it's kind of believed that at the end, the question of where to put the cut is just a philosophical one. And at the end, doesn't matter if you are talking about things we can really compare. However, this is not so clear. And more recently, people have started to study what I call multi-agent scenarios. And I'm by far not the only one studying those. There's, for example, a similar study by the group of Czeslaw Bruckner in Vienna. And one considers essentially the question whether, if you have several agents, can it happen that if they all apply quantum theory, the accepted formalism, but they put the cut differently? So for example, this agent here says, that's my quantum system, and the rest of the world is classical, and that agent here says, no, this is my quantum system, and so on. Could it be that there will be some contradictions arising? Now the answer is yes, there can be contradictions under certain assumptions that are very natural, and this is worrying. So this is, by the way, the reference for this, and you see in the title says quantum theory cannot consistently describe the use of itself. So this is really referring to the fact that, for example, this agent here would describe how this agent uses quantum theory to describe this particle. That these are questions you can ask. But to relate it to this communication setting, let me say the following. So as as I said before, this agent may treat this thing as a quantum system, but not the rest. So this agent may still be in the same classical realm, if you like, as this agent here. So they can communicate. And the same may be here. So this one can communicate with that because this guy doesn't see her as a quantum system. And so I get arrows whenever I have two people who consider themselves to be in the same classical domain, or whenever they jointly think they are outside of this Heisenberg cut that I mentioned. And now one can analyze this and say, okay, these people can now talk to each other. Do they actually arrive at consistent conclusions? And the answer is no. More precisely, one can prove a theorem, and the theorem says that if each of these agents apply quantum theory, but they make different choices of what is really the quantum system and what is the classical realm, and they communicate whenever they are jointly in the classical realm. So this means that, I mean, communication means you can not only communicate, but you also take the statements that someone else makes and tells you as serious statements, then you can then you get a contradiction. There's also a third assumption, which I don't go into here, because I think this is just essentially saying that when we measure something, we can believe, these outcomes should be taken as facts for at least the person who measures them. So that's certainly something that is undisputed. But the theorem tells you that we cannot at the same time apply the current formalism of quantum theory and still have this communicability. So these two things are actually contradictory. And that's, at least for me, a big problem, because of course we want, I mean, this statement of Bohr, I think, is very important. When we do physics, we want to have the ability to essentially communicate and be consistent when communicating. So if I'm talking to my, let's say, friends in Innsbruck, to Hans Briegel, I communicate to him something, and then I hope he takes it as a credible claim, and you can use that claim in his own deliberations. And that's essentially how science works. So I would like to take this as an assumption, but if I take this as an assumption, then the theorem tells me I have to give up this. So what does this mean, or how could it be? I mean, I just said before, quantum theory is an extremely accurate theory. So how can I even dare to say that there could be, I mean, this assumption could be wrong? Now, there is a very, let's say, clear way in which one could say the way we are applying quantum theory is actually a special case. And this special case is the following. So when I do a measurement, I'm myself a macroscopic big system. And I could say, I'm, for example, if this is the wave function in space of myself, I'm a perfectly localized system. So I'm talking about me being this person A here. So when I consider another, when I describe another particle, I usually mean, for example, when I talk about the position of this particle, I mean the position relative to me, but because I'm well localized, as I think, I just take this relative position as essentially the value of where this particle is. But now, suppose I'm myself a quantum system, and that's of course relevant in these setups I've just shown here. I mean, this thing is now a quantum system from the viewpoint of that agent. So suppose I'm a quantum system from the viewpoint of someone outside. So if I'm a quantum system, I can in principle be in a superposition of states, of positions. I can be here and here in a superposition from the viewpoint of an outside agent. And the question is now, if I'm myself in a superposition, of course, I don't maybe feel myself that I'm in a superposition. What would I say about this particle here? And the answer, I think, is pretty clear. And this has been pointed out by many works, again, by actually the group of Czaslaw Bruckner, as well as people stemming from this group, and also by older work by Popescu, Angelo, and others. The answer is essentially this one. If A is in a superposition of positions, but takes herself as a reference point, then even if from Wigner's viewpoint, this particle is localized relatively well, from the viewpoint of Alice, who sees herself as a fixed point, this particle appears to be in a superposition. So in other words, whether something is in a superposition of or not is now relative to the person. This is not surprising. I think this is in some way very natural conclusion of taking quantum theory seriously. But now comes the problem. When we developed quantum theory, we never did it under the presumption that we as experimenters are themselves quantum systems. So we are really in the restricted regime where we are always looking at the world from the viewpoint of a classical macroscopic reference that cannot be in a superposition. And so the question is, how would the world really look like if the experimenters, if the agents themselves are quantum systems that can be in a superposition? And maybe the formalism that we get then is more general than the current quantum formalism. And maybe the generalization is such that this contradiction that I mentioned here will no longer arise. So that's the connection to what I said before. And this brings me now to, this was the first part, and now comes the shorter second part. So this brings me now to the question, how can we find out how the world looks like if we were ourselves quantum agents? And this is also the part where I am thinking for a long time about this question, essentially became more and more desperate. And at some point we said, okay, it's really hard to think how the world looks like from a quantum perspective, from a perspective of a little agent that is so small that it can be in superpositions. But maybe we can get some help from machine learning. And that was essentially a long time ago when I entered this field, but now you see there's this connection. But the connection goes a bit further. So the connection really goes back or now brings in again this notion of communicability. So the goal that we wanted to achieve first is, of course, not to solve this question. This is a very hard question. How does the world look like from a quantum agent's perspective? Of course, the first question you have to solve if you go into that direction is, can you make a machine that at least reproduces current quantum theory as we know it? I mean, we have to kind of have a test case. And of course, we know how quantum theory looks like from a macroscopic agent. So the question is, can we reproduce that? Or what could we learn if we had a machine that just tries to reproduce the theory? And now you could think of the following setup now in the spirit of what Bohm said. Let's suppose Alice is now, in this case again, back in a macroscopic agent, and she does an experiment with some small quantum system, like a spin that is emitted by a source. And maybe you have a source that can, for example, produce many copies of the spin and so on. Now, the whole point that Bohm made is that, and what we want in physics is to have something, I mean, we cannot really say what that is, but we can give a description to someone else. So we can talk to someone else in a language, and the language should, or what we tell another person should allow this person to also make statements about these systems. So for example, the second person, Bob here, may get questions from someone else, like, for example, the question could be, what would have happened if I measured this system in a particular basis or according with a particular measurement device? And then if Bob here got a good description of the system from Alice, then he should be able to give a correct answer to whoever asked this question. Now, our idea was the following. Let's suppose that we minimize, I mean, we want to essentially say this communication is the expensive resource. So let's try to see whether we can, what does Alice need to tell Bob about the quantum system if she wants to give her a minimal amount of information, but still information that allows Bob to answer the relevant questions about this system. And what, if we translate this question into now representation learning, we get something like that. So maybe it's not obvious how this is linked to what I said before. So I have another picture which brings back the agents. So you could think of such a network. I guess you're familiar with such representation learning networks with an encoder and a decoder. The idea is to regard the individual parts of the network as different agents, and some parts of the networks which are constrained in the number of neurons by the communication between them. So we have somehow in this network now units that count as the agents and other parts which count as the communication between them. And now we can say, okay, that's now gives us a clear instruction what we want to optimize. So we want to be, we get here the experiment. Alice does this experiment with the qubit or with the spin particle, and here she, Bob wants to give answers to some person who asks questions. This can now be implemented, and so again, that's just the network structure. You have now kind of a network. We call that SciNet for scientific network, and you can now start to do experiments with that. And
Renato, you have about 5 minutes, okay?
Yes, thank you. So the first experiment, and now I should stress these are really toy examples. So I'm not claiming now that we can go into the realm of getting new physics yet. We are far away from that. But as I said, the first goal was to at least reproduce, to have a machine that without or with minimal prior knowledge can reproduce somehow what we already know about quantum theory. So this is again the setup that I've shown you before. So there's this communication setup. And now we could ask the question, what happens if, for example, this is just a 1-qubit system? That's the simplest possible toy example. And we now want to minimize the communication. So what's the best way for Alice to tell Bob what is the state of a quantum system? Now, I should emphasize that when we now trained this network, we didn't tell the network anything about quantum theory, of course. So the network just gets experimental data. It can essentially do, if you like, experiments with this qubit. And then it has to give Bob a description that is as efficient as possible so that Bob can again answer questions from these third persons about other measurements that one could have done on this system. And what this experiment told us, what we found when we trained the network, is that Alice can communicate to Bob with, I mean, this is the number, here is a number of latent neurons, and this graph shows how accurately or what's the error in the answers that Bob gives to this questionnaire. And you see that as soon as we have 2 neurons, so these are the neurons here in between, this corresponds to how many parameters does Alice communicate to Bob. As soon as we have 2 parameters communicated to Bob, the error becomes very small here. So this tells us something that was, of course, known about quantum theory, that if you have a qubit, and here we considered only pure states, then this is described by 2 real parameters. Now, this, of course, also works for larger situations. So this was the case for 2 qubits, but then our method already becomes a bit slower, but we could do it. And here we found the correct answer, or at least what the answer reflects what we know about quantum theory, that in order to describe 2 qubits, we need 6 parameters. We could also extend that further, and that was in the recent work I did with Hans and his group. We could, for example, look at a much more involved communication scenario where this party here makes an experiment with a system that consists of 2 qubits. But now, instead of, I mean, in contrast to the situation before, there are now different people who have different interests or different tasks. So, for example, this guy here may only want to answer questions about this qubit here. And the lady here only wants to answer questions about this qubit, whereas maybe this person really wants to answer questions about joint stuff you can do on this system. And now in the same way as before, we could impose the constraint that we want Alice here to find a description of this, but now a description that is more fine-grained and structured in such a way that she can only send always the relevant, just the relevant information to the persons who need them. So maybe this guy needs fewer description parameters than this guy, because this guy is only interested in that part. And the result here is again that we reproduce exactly what is known. And that's, by the way, a surprising fact about quantum theory, that if we know, if we have a full description of this, so the full description of this, if it can be a mixed state, is given by 3 parameters. That's a Bloch sphere representation. Here as well, 3 parameters. So what they need are 3 parameters, whereas the total description is not, as one may think, 6 parameters, this plus this. It's actually much more, it's 15 parameters. This is because we only also have entanglement in a quantum system. And that's indeed what we found. So what this graph shows is the type of results we get. So we can think here of this communication as represented by neurons as before. And then we can ask ourselves what is actually stored in these neurons and how many of them are really used. And now if you, for example, consider for the left qubit, for the one that goes here to this guy, how many parameters are there that determine that qubit? Then we find there are only 3, and the others are unused in a way. This is just reflected by having some noisy thing here. Okay, so that brings me almost to the end. I just want to, so I think my main message is the following. This notion of communicability that was introduced in the context of foundations of quantum theory, essentially to make sense of what is an experiment and what is the classical realm and what does it even mean to physics in that sense, in a quantum world. This notion of communicability seems to be quite usable and actually powerful in the context of training networks and motivating networks to find meaningful representations. So another example that I just want to mention and not go into the details, but to illustrate that one can push this approach a bit further, is we can not only constrain the amount of communication that goes from one party to the other, but we can also constrain the computational power that is needed by the party to make predictions based on the description. So here is an example where we say Alice has gets some description of the position of Mars from the Earth viewpoint, and then her task is to communicate the position of Mars to her colleague, but in such a way that the effort he needs to reproduce and to make predictions is minimal. And then it turns out that, again, if you encode that in a network similar to what I explained before, what Alice does is actually communicate the angles as seen from the sun. So in other words, the network somehow realizes, of course, implicitly, I mean, it doesn't tell so, but it finds a representation that is corresponding to the heliocentric viewpoint. And that's again based on this idea of communicability. Okay, so this brings me to my conclusions. And the conclusion, I think I already mentioned before. I think it just shows that there's a big common let's say, notion in AI and in foundations of physics, this communicability, which plays a role to define the Heisenberg cut in the foundations of physics, but which at the same time can be extremely useful to make sense of representations and to motivate networks to produce meaningful representations that help us learning concepts. And I end here with this citation I mentioned before from Bohr, which is really somehow at the core of what I told you. Okay, thanks a lot for your attention. And I'm very glad, or I will be happy to take questions if there are any.